welcome back to our lecture series on algebra. From our last section, we looked through the types of algebra, and in this series I'm going to take that of the operations of matrix algebra. Okay, with the operations of matrix, we are just looking at the regular operators in mathematics, nothing new. So we can still add, we can still subtract, we can still multiply, divide, and even find something called determinant. This is what I'll be taking you through. So you stay with me with my slides and my notes. I think I would want to expand the notes for now. Where I need the slides, I'll let you see them. So let me change it to green. Yeah. Let's first start with addition or subtraction of matrices. Addition is this sign and subtraction is that sign. We already know. And what kind of matrix can we add or subtract? We can add a row matrix. We can deal with a column matrix. We can deal with a square matrix and then a rectangular matrix. We already know this from the previous lecture slide. Okay. Before we can add any of these forms of matrices, there's a property or there's a rule we must follow. That rule says that these matrices must have the same or equal dimension. Dimension is the same as size. You know that. Equal dimension before you can add or subtract them. So let's take a quick example here. Before you do operations, you must classify or determine the dimension of your matrix. This matrix here is 2 by 2. You'd want to confirm. Why? Because we know. This matrix here is 3 by 2. Can we add them? No. Can we subtract them? No. Why? Because the dimensions are not the same. They are not equal. So we can't add them. Let's take this example 2. This is a 2 by 2 matrix. This is also a 2 by 2 matrix. Can I add them or subtract them? Big yes, because they are the same. The dimensions are the same. In the third example, this is, I think, 3 by 2. And this is also 3 by 2. Can I add or subtract? Yes, I can add them because the dimensions are the same. So this is how simple additions and subtractions can be, by checking the dimension of the matrix. Then the next question you want to ask yourself is, how do I add or subtract these matrices if I can't find the dimension? So I'm going to take a simple 2 by 2. This is 2 by 2. This is also 2 by 2. And so I can add them. When I add them, I'm simply going to get 2 by 2 because it's the same dimension. We add them 10 by 10 or element by element. You know, elements are some aij's. Assuming this is a capital A matrix, this capital B matrix. It means I add or subtract by bij. And this is what I have done here. So this first number would add to this first number. And that is what I have here, or subtract. This second element will have to take this second element. And that is what I have here. This one here would have to also add or subtract the term here, and that is what I have done here. And in the last term, take this guy. And so this is how we add or subtract matrices, term by term. Don't forget this preamble here, aij plus bij, or aij minus bij, and that is all. Let's take an example here. This is 2 by 2, 2 by 2. Since they are equal, I can add them. So this adds to this, I'm going to get 4. This adds to this, if my additions are right, I'm going to get 12. This will add to this, giving me 8, and then this, and then the last term gives me 10. This to 2 by 2. This is how simple addition and subtractions are done. So you can just take the same matrices and find the subtraction, and let's see what we are going to get at the end of the day. You can take that answers in the comment section for me. If I subtract the same matrix A and matrix B, what do I get? That is the first operation, addition and subtraction. The next operation I'm going to take you through is a transpose operator. As the word suggests, transpose, it's like a reverse. And so if I have a row vector, you know why it's because I have one row by some n columns. If I transpose it, I should get n by 1. This should give me n by 1. That is a transpose, so it becomes a column because I have one column by some n rows. So every row becomes column. Likewise, a column will become row. Okay. If I have a rectangular matrix, this means n is not equal to m. N can be less than m, or n can be greater than m. We've gone through this. If I take the transpose of it, the rectangular matrix still maintains, but the dimension just changes. So I end up getting m by n. So an example would be, let me take the transpose here. If I have 1 and 2, the transpose will become 2 and 1, row to column. In this example, if I have, let me have enough space for myself, so the rectangular shape will not change, but the dimension would change to m by n. Example, if I have 2, 3, 4, 1, 5, 0. This is a rectangular matrix. The transpose of this, every row would become a column now. So I have 2, 3. Every row will become a column. So 4, 1. Every row becomes a column, 5, 0. And what do you see? 2 by 3, no, 3 by 2 now becomes 2 by 3. And that is the transpose. So it means that here the row here became a column. So 1 by 2 is supposed to give me 2 by 1. And that is it for transpose. Okay. If I have a square matrix, what do you think the transpose would be? I'll end up still getting a square matrix. So example, if I have 2, 4, negative 1, 5. The transpose of this becomes, this row becomes a column. So I have 2, 4. This row becomes a column, negative 1, 5. What do you see? I still have 2 by 2, 2 by 2. What happens is that the element changes their position. That is all. Just like the rectangular and then the row. In square matrix, dimension does not change. That's one interesting thing about square matrix. But the element changes position. So you can see this was A11, A12, A21, A22. But now it has changed to, see where A12 is, it is now here. And A21 is now here. It has changed positions. The last thing I want to do under transpose, if I have a column, I've already talked about this. It's column because I have one column. This will end up becoming a row vector to give me 1 by n. So it just changes. An example is I have 2, 3, 1. There's a column vector. It has 3 by 1 rows. The transpose should give me a row, which will be 1 by 3. 3 by 1 becomes 1 by 3. And so I have the column turns to a row, 2, 3, 1. Please, I forgot to stress that rows do not take commas. This is not a matrix. There's no comma in it. Alright, so you take note of the representations as well. That is just how simple transpose it. So let's see. If I have 2 by 3, the transpose becomes 3 by 2. If I have 4 by 4, the transpose remains 4 by 4, but the element changes. If I have 1 by 3, the transpose becomes 3 by 1. If I have 4 by 5, the transpose becomes 5 by 4. Do you see the trend now in the transpose? Okay, thank you very much. Let's take the third operation. That is a scalar multiplication. What does scalar multiplication do? It just multiplies the scalar. So I can use a square bracket or a parenthesis. It just multiplies the scalar by the element in the matrix. That is all. So it's like a dot product. So example here, this will be 2 by 1, 2 by 0, 2 by -1, and then 2 by 2. If I expand this, we get 2, 0, -2, 4. So the dimension would maintain, but the element will change. It's not the position of the element changing, but the values in the same position changes. In place of 1, 0, 4, -1, so I'm now getting 2, 0, -2, -4. No, sorry, +4. So that is how scalar multiplication is. It can even be a bigger matrix. Let's say 1, 2, 4, 5, 6, 7, multiplying -1. I have to just multiply every number by -1. So I'm going to get -1, -5, -2, -6, -4, and -7. This is how simple scalar matrix multiplications are. The most interesting thing with multiplication is the matrix multiplying itself. Unlike the scalar, there's a condition or property that we must follow, just as we did for the addition and subtractions. In the matrix multiplication, I have matrix A as A by N by M. I have matrix B as P by Q. I can only multiply these guys if the inner dimensions here are equal. That is to say that I expect M to be equal to P to say I can multiply them. If I'm able to do that, then the resulting matrix A times B will end up being N by Q dimension. So the outer ones becomes the resulting matrix. Okay, if and only if the inner are equal. So let's verify this if you can multiply them by the rule. Can I multiply this? Yes, because the inner dimensions are equal. Can I multiply these two matrices? Yes, because they are equal. Can I multiply this? Yes, because the inner dimensions are equal. 3 is equal to 8. Can I multiply this? No. Why? These are not equal. I have 2, I have 1. Let me just do the resulting matrix. If I multiply this guy, I'm supposed to get 2 by 2 at the end of the day. If I'm able to multiply these guys, the outer ones becomes 3 by 2. If I'm able to multiply this, as I said yes, then the resulting matrix is 3 by 1. That is a row vector. This is a square. You believe that? This is a rectangular. This is a row vector. Since I can't multiply, then I don't have any resulting thing. Can I multiply this? Another big no, because these inner dimensions are not equal. So that is how beautiful matrix multiplications and easier is. Just check the inner dimensions. Okay, so let's take a quick example here. Can I multiply these two? Let's check. This is 2 by 2. This is 2 by 1. I'm sure by now you are conversant with the dimensions of matrices. Okay. Can I multiply this? A big yes, because the inner dimensions are the same. And what do I get at the end of the day? I'm supposed to get 2 by 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1 Then the next question you want to ask yourself is how the multiplications are done. Unlike additions, I will take it term by term. Matrix multiplications do not go by that rule. What matrix multiplication does is it takes one row and multiply, I don't know which number was here, I deleted it, and by this column. It takes the second row and multiplies by the same column. So this is what you're going to get. I have 1 2 multiplying 2 1, and I have the same 1 2 multiplying the same 2 1. This should end up giving me 2 rows by 1 column. You can verify this. Let me clean this one. I know I'm supposed to get 2 by 1, and how do I get it is by this way, each row multiplying a column. And let me see if I can help you with the answer. So I have 2 by 1 plus 2 by 1. I have 1 by 2 plus 2 by 1 here. So this is 1 by 2. This takes that plus this takes that. This takes that plus this takes that. And that is how the multiplication is done. So I end up getting 2 plus 2, that is 4. Oh, I'm wrong. And then this gives me another 2 by 2, which is 4. Please check this answer for me. Alright. And this is simply 2 by 1 as we expect. Let me take the second example here. Can I multiply them? I have to check the dimension. This is 2 by 3 and this is 3 by 2. Yes, I can multiply them because they are equal. And the resulting matrix after multiplying is going to be 2 by 2, which is a square matrix. How do I get the square matrix? I'm going to take this row and multiply by this column. So I have 1 2 3 multiplying 7 9 11. The same row will multiply the second column. So I'm going to have 1 2 3 multiplying 8 10 12. I'm not done. I expect 2 by 2. The next, take the second row, multiply by the first column. So I have 4 5 6 multiplying 7 9 11. And then the same 4 5 6 we'll have to multiply 8 10 12. You can take your time and see what these answers would be. I'm supposed to get a 2 by 2 matrix. And that's how simple it is. Again, I'm going to get 1 times 7 plus 2 times 9 plus 3 times 11. That is how it's going to be. 1 times 8 plus 2 times 10 plus 3 times 12. So I add them. 4 times 7 plus 5 times 9 plus 6 times 11. This is how you do your multiplications. That is a quite easy one. You can do that. Let me check the next operation. I think that's the last operation. Is the determinant. The determinant of a matrix. Notation wise, we can use this, or some will say that of the function a. These are all the same. It is not square. Even if you say square of a is a different thing, or parenthesis of a is a different thing. Either you use the absolute or the determinant, det. Even some textbooks use capital Det. Yeah, they are still correct. If I have a 2 by 2 matrix, as you see here, the determinant is given by this. Multiply here and subtract by this. If I have 3 by 3 or more, 3 by 3 or more will follow the same procedure. So, or more. Let me add this for you. What we do is to use this minus, plus, negative, plus, because it's just 3. If it's 4, it follows. What we do is to take these guys as your coefficient. So I take A out. Because A is here, I cross these guys out. And what is left, I write E, F, H, I. Wherever the A is on first row and first column, so I cross it out. Then I come to take minus B. In minus B, I will have to now cross this row because B is here and it's here. What is left is D, F, J, I. Okay. When I take C, what I'll have to cross is C is here on the third column and it's on the first row. So I end up getting D, E, J, and H. And these are just 2 by 2 determinants. That is given here. So I'm going to get A out, EI minus HF if I'm correct. I'm going to get negative B out, DI minus JF. And this will give me C out, DH minus EJ. And then I find a final result. I think I have an example for you to make life easier. I have the first 2 by 2. You realize I have this stroke here to tell you I'm looking at a determinant. So this is going to simply be 3 times 4 minus 7 times negative 2. 3 times 4 I think is 12 minus 7 times 2, that's negative 14. I'm supposed to get 28 or 26 because negative and negative become positive. So I'm going to get 26. I'm sure about this one. Again, you can verify. If I want to go to 3 by 3, what do? I'm going to use plus. So plus, minus, plus. Okay. So 1 here. I cross this and that. 5, 6, 8, 9. If I take it out and I go to negative 2, I'm going to cross second column first row. And that's 4, 6, 7, 9. If I want the third position, I take 3 column and then first row out. 4, 5, 7, 8. And I find the determinant using 2 by 2. You would want to see what you're going to get at the end of the day. Whatever I get here, I add it to whatever I get here, plus whatever I get here. That is how simple this is. I'll show the answers in my slides, but now you want to understand it for me. Okay. Let's take properties of determinant. Properties of determinant. If I have the determinant of a scalar multiplying a matrix A, it is just given by Kn and then the determinant A. What this one says is that do not worry yourself to multiply through the scalar. Just take the dimension of A out to the power of the scalar and then find the determinant of A. I hope that is well understood. So assuming I have 2 times A, it will be 2 to the power n determinant of A if I'm finding this. Where n is from the dimension of A. Okay, I will take an example and then we'll see. If I have A transpose and determinant, we want to believe that it's the same as the A transpose. Why? We will take an example on that. If I have the determinant of AB, it's the same as taking the determinant of A and multiplying by the determinant of B. This is how smart you want to be. And so you don't want to go through matrix multiplication before you go ahead and find the determinant. What you want to do is find the determinant of A, whatever you get, multiply by the determinant of B, and that is all. Okay, I think that is all with the properties. So let's take a quick example here. I have A to be that. If I want to find the determinant of A, there's 2 by 2. So I'm going to get 4 minus 6, and that gives me negative 2. What is A transpose? A transpose, a row becomes a column. So I get 1, 2. A row becomes a column, 3, and then 4. And what's the determinant of this? I'm going to get 4 minus 6, that is negative 2. Are they the same? Yes. And so the property here is fulfilled. So if you have a matrix and you want to find the determinant of its transpose, it's the same as the determinant of the main matrix. That is what the property says. Now let's look at the scalar multiplication of the same A. 2A, I'm going to get 2, 4, 6, I'm right, and then 8. Okay, let's look at the determinant of 2A. This is going to give me A2, 2 times 8 minus 6 times 4. And that is going to be 2A 16 minus 6 times 4 is 24. I hope I'm right. And that results to negative 8. Negative 8. Is that correct? I'm not so sure about that, but let's see what we can do. Let's continue. We want to verify. So assuming I don't want to go through 2A first, it says, what's the dimension of A? Dimension of A is 2 by 2. Okay, there's the dimension of A. It means 2A, I'm expected to get 2 to the power 2 and then determinant of A. I've already found the determinant of A, which is negative 2. So this is the same as 2 to the power 2 times negative 2. Determinant of A is from here. If that is wrong, it means our answer would also be wrong. And that's going to give me 4 times negative 2. Hooray! That is negative 8. Are they the same? Yes. So this is how smart you want to get. You might think this is, why would I want to use these properties? It will become handy if you have a higher dimension matrix. So assuming my matrix is 4 by 4, I have 2, 3, 4, 5, 1, 0, 1, 1, negative 1, 2, 3, 4. I want 4 by 4. 0, 0, 1, 2. And then you are asked to find assuming this matrix B, you have to find the determinant of B transpose. My dear, you don't want to worry yourself to find B transpose first before you can find the determinant of B transpose. Don't go through this wahala, no. By properties of determinant, this B transpose is the same as the determinant of B. As simple as that. So you see how handy this becomes. Again, if I was having 4 multiplying B, you don't want to find 4B and then go ahead and find the determinant of 4B. That'd be so much work to do. You don't want to go through this. Let me use red ink to stress. You don't want to go through this. You don't want to go through this. No. Big no. What do you have to do? It says find the dimension of B. Dimension of B is 4 times 4. Okay. So raise this 4 to the dimension of B and then find the determinant of B. And that is all. Given that B is a square matrix. Because I'm sure someone will ask, what if my B is not a square matrix? How do I find that? Then you have to go through the process. Alright. So that's how handy these properties may be for you. I thought I was done with the properties, but I think I have the last one, which is the inverse. Inverse is when we are doing the divisions, like having A over B. In matrix, we can't do just division. It rather becomes A times the B inverse. And that is where inverse come into play. So if I have 1 over B, 1 over A, I can simply write this as A to the power negative 1 by indices, and that is the inverse. Inverse is given by, we know this guy now, that is the determinant, and then times the adjoint. In other textbooks, the adjoint is written as this, adjoint of A. Alright. Now, you would want to know when you can find A inverse before you go through the wahalas of finding A inverse. A inverse would exist if and only if. So IFF in math is if and only if. If and only if my determinant is not equal to 0. Why? Because I have 1 over the determinant times something. Whatever I say, I don't care. If I have immediately the determinant go to 0, it's like having 1 over 0 times something. 1 over 0 is undefined. So that is why if your determinant is 0, then you can't even go ahead and find the inverse of the matrix. You want to take this property very serious. Okay. So I want to try 2 by 2 inverse. What will be a determinant? I know determinant of this is going to be AD minus CB. The adjoint, I've already found the adjoint here. Wow. So what we do is we interchange positions of these guys. So D comes here, A comes here, and then we just negate these guys. Negative C, negative D, and that is it for inverse of a matrix. I know you can use calculators to simply do this, but you want to know by hand and then the properties to use. I think on this note I'm done with my operations, but let's see the answers for the other operations I didn't show. I want to quickly move back right from addition. If I had something to show you, I think addition was fine. Addition was fine. We didn't have anything to show in addition. Okay, there was an example here. Let's look at transpose. I did everything under transpose for you. Scalar multiplication too I did. Matrix multiplication, I think that is where I had a gap to fill. Yeah, I have a gap to fill here. And so let me quickly move through my slides to where I have the matrix multiplication. Everything I have on the slide is what I did on the sheet, so be cool. Alright, be cool with me. Matrix operation, where are you? Oh, I didn't have an example on my slide, but at least I've tried my best to have an example on the sheet for you. So let's find the answers here. Okay, I've shown you what to do. Determinant, then I think that is it for the lecture series. I've virtually solved everything I want to do. Determinant, where are you? Did I take an example? Yeah, it says the answer is 0 for this guy. The determinant of this guy is equal to 0, but I didn't finish, so you want to please verify for me. These things here are not 0. There are some boxes I need to find. Okay, there are some boxes I need to find. Should I go ahead and solve that for you? I'm not sure I'm ready to do that, but you'll be fine. Just go through them. And that brings me to the end of my lecture. Okay, on slide 12, I've given you some matrices to test on. I just used the matrix A to test the properties. You can try the other properties and then see. Especially, I didn't verify this one. I've given you A and B. It says don't expand, don't find A, B before you go ahead and find the determinants of A, B. If you can find them separately, they will be equal. So kindly do the test for me and see what we are getting. I'm sorry to say I'll have one more lecture video on matrices, which you would love. That is going to be on applications of matrices. I have several problems for you and we'll take the solutions of these problems. And so permit me to have one more lecture video on matrices. Again, if you've not subscribed to the channel, the YouTube channel, you want to do that for me to have updates. Thank you very much.